He was born just 31 years ago in Rio de Janeiro, Brazil. Very early, he went to IMPA, Instituto de Matemática Pura y Aplicada in Rio, where he got his PhD in 2001 under Wellington de Mello. He is now a professor at IMPA, as well as senior researcher in CNRS, the French National Center for Scientific Research, working in Paris 7. Artur is one of the best experts in dynamical systems, especially in low dimensions. He belongs to the category of problem solvers. Many of his papers are masterpieces, tour de force. Artur likes to work with others. With Jana, he proved the Kontsevich-Zurich conjecture on Teichmuller flow. With Forni, he proved that almost every interval exchange is weakly mixing. With Wiesel and Yokos, he proved that the Teichmuller flow has an exponential decay of correlation, etc., etc., etc. Today, he chose to discuss renormalization dynamics. This has many historical roots from very different horizons. You will see that among his talents, Artur has the ability to merge seemingly different areas in a single coherent topic. Only the very best mathematicians have this ability. Artur, listening to you.
Okay. Thanks, Etienne. So indeed, the renormalization ideas permeate several branches of mathematics and physics, and it would not be very wise to try to enumerate such branches. But in any case, this talk is about specific incarnation of those ideas, namely renormalization as a tool in the analysis of dynamical systems. There will be a question of what's dynamics, which is again something that perhaps I shouldn't, to be smart not to try to answer, try to give a definite answer. What I can certainly say is that many dynamical systems, many dynamicists like to iterate maps. So, let's say, okay. So they iterate maps, so they look at the dynamical system as kind of a map acting on a space, and they think of this as in a moment of time, something happens, and then let time go by, and what they typically do, take an orbit here, a point, and start iterate around. So you do it several times, and soon you get a cloud of points. And they might ask some questions such as, where does this cloud go? So there's some kind of limiting set where it goes. Another kind of question would be, how is it going to be distributed in this limited set? And then so very different kinds of questions. Sometimes one is interested in some kind of looking on a microscope. So one is actually interested in what dynamics is doing to a small region of space. So in this situation, there is a common technique to do this kind of microscopic approach, which is kind of inducing. So inducing is the following, is very general tool. You start with a space X, with some dynamical system X, but you're really interested in some smaller region Y. It's not too small here, but imagine a very small region. And now orbits might start at Y, and go on, and sometimes return to Y. They might return at different times, but you have this. You have this set of orbits that go to Y. You look at these moments of passage. So in this procedure, forget what happens outside, and just look at this kind of map coming from Y to Y. And by the analysis of this map often reveals lots of information. And this can be a very successful approach. Now, this is a very general procedure. You can always do this with a dynamical system. And generally, the kind of induced map that you get has nothing to do with the original one. Looks perhaps much more complicated. And sometimes has better properties and so on. But in some kind of very special circumstance, something remarkable happens that this dynamical system in the smaller region looks like the dynamical system in the larger region. And this is what we call a renormalized situation. So here we take that kind of map again. And what you see is that, you can take here the second iterate of the map. And you found out there is by looking at this box, that there is this little interval corresponding to this box coming back to itself in the second iterate. So you can consider an induced map that looks like this. And it looks like the original map. In which respect? Well, perhaps the original map was a quadratic map. This new map will no longer be given by a quadratic equation, so it's not this, the quality that you're looking for. It's just here the shape of the map. Here, this map in this small box is again new model as the original map, which means that it has a single critical point, which is an extremal. Now, what we can do here is rescale space now to get a map that basically acts on the same space as before. So you do this procedure. So renormalization certainly involves some rescaling of space. Should also keep in mind that you are rescaling time as well. Because let's imagine that one heartbeat for the renormalized map on the right corresponds to 2 heartbeats for the original map on the left. So you rescale time in this direction, and on the other hand, you do the more or less opposite with space. Okay, so once you have the renormalized map, of course, you start iterating again, and you might find out that it is itself renormalizable. And in this situation, you have this kind of secondary renormalization. What it's going to be telling you is information about the original dynamical system in a yet smaller scale of space. That's indicated here. And then by iterating renormalization, we're going to get more and more information about deeper and deeper regions. So now, some kind of formally, there are in principle many ways to renormalize that would work. A renormalization operator corresponding to the fixing of a specific way to renormalize, a preferred way to renormalize. By doing so, you get a map, well-defined map, on a certain class of renormalizable systems. And then what happens is that I should say that, of course, I said that you need to iterate, but one thing that's kind of not obvious, but my job is to try to convince us that might work, is what I think of as renormalization ideology. That it's useful to try to understand, or it works, let's say it's an efficient way, to try to understand this kind of small-scale behavior, the dynamics of the class of renormalized maps, by trying to see phenomena as reflections of interesting aspects of this dynamics in parameter space. So it gets kind of meta-dynamical system, a dynamics on the space of dynamical systems, and somehow its dynamical properties reflect on the dynamics of the original map. So I'd like to discuss just a few themes before moving on to specifics. One finds out that the success of this ideology is not going to work always. Usually, it works in low-dimensional situations. I like to think of it as kind of, there's no kind of formal statement about it. That's a formality issue. That if you don't work on things that are not conformal, there are several intrinsic scales at the same time, spatial scales. And maybe they are not coherent in space. At some points, they may be pointing in some direction, and others there might be some kind of other directions, and there's no kind of natural way to scale generally. So that's why I don't want to emphasize much this point, but we're only going to see low-dimensional systems in this talk. Another aspect that I can explain better is the low complexity characteristic of the renormalized dynamical systems. What is low complexity? One way to measure complexity is entropy, but it would be a little bit difficult to define it appropriately. Another, very closely related, is by the Lyapunov exponent. And so renormalized systems have tend to have zero Lyapunov exponents, the ones that will work fine. So Why is it? It's a very simple mechanism that shows the effect over scaling of time. That Lyapunov exponent, what is it? It just measures the rate of exponential growth of the derivative, of the iterates. Ignore for the moment the issue of existence of such kind of limits. Let's imagine it exists. You have this Lyapunov exponent, and the effect of time rescaling, since each heartbeat of the renormalized map corresponds on average some certain number bigger than one of iterations of f, the Lyapunov exponent of the renormalized map will be some multiple bigger than one of the Lyapunov exponent of f. If the Lyapunov exponent is non-zero, then it will just go to infinity or minus infinity, and you're going to have divergence or normalization. No interesting dynamics may take place. So this kind of strategy of looking at dynamic phenomena is not going to work. So that's a good. So there are some systems that you should forget to try to normalize. One was seen in the last ICM. And that's the Lorentz factor. I don't want to say much about it. But it's kind of a very beautiful example of a system which has positive Lyapunov exponent with sensitive dependence to initial conditions. So the orb stayed originally nearby, and then they start separating exponentially fast. So that's one example I don't want to discuss. It's specific. Let's show another one that will appear later in the talk. This is map that I call it the binary expansion map. It's closely related to binary expansion. If you start iterating, you're going to start decomposing your interval like this. This map clearly has the derivative constant equals to 2, so the Lyapunov exponent log 2. So this map is not going to be one normalized. So, okay, so normalization is not going to be used for those maps. That's not a problem, because those maps have what's called the good chaos. Good chaos that means that brings things like independence into play. So things are mixing up so fast that phenomena start becoming independent as times separate phenomena. And independent brings into play so-called probabilistic techniques, for instance, that are much easier to deal with than the usual deterministic techniques that you have to deal with if you don't have some independence to play with. So those, let's not worry about those systems, they have their own technology to deal with. Now, I would like to mention something now about the renormalization dynamics, which opposes a little bit the normalized dynamics. First observation is that renormalization will tend to act on infinite-dimensional functional space, except if you're renormalizing linear systems that are described by finite parameters. But for instance, even if I'm renormalizing those kind of unimodal maps, I start a quadratic map. As I start iterating, I get things degree 4, 6, 4, 8, and so on. And in this way, I'm immediately forced to incorporate, to do the analysis in an infinite-dimensional space. It will be the appropriate setting. So this contrasts with the one-dimensional nature of the original system. On the other hand, there is one good thing that we often will find a renormalization attractor. It's extremely important. The renormalization attractor means that as you, so there is some kind of small region of space, just some kind of little place in that huge infinite-dimensional space. And as you iterate renormalization, orbits will start approaching this attractor. The way that this affects the dynamics of the original map is that this is constraining the small-scale behavior of original maps. Once you normalize and look in a very deep scale, you are no longer going to see something that might be anywhere in your original possibilities, but just something that's in that very specific region. This is often associated with so-called universality phenomena. You're always going to see the same thing, what's happening in that attractor. So that's another theme. And of course, once you have the attractor, you're going to try to describe a little bit the dynamics there. And it turns out to present often some kind of good chaos, the one that we're talking about, and brings into play those kind of probabilistic techniques that are very powerful for the analysis of parameter space, for instance. Now, that is certainly very important for the renormalization ideology, because certainly for me, when I first started hearing about renormalization, I thought that it was a very bad deal, starting with a one-dimensional map with low complexity, and then get to an infinite-dimensional map with large complexity. That kind of, but this large complexity is helping you, and it's much easier to do this analysis as the original map directly. So that's one thing behind One last thing that's kind of very simple remark, but very is a theme that you frequently encounter, and I won't be able to discuss in details, is the importance of a priori bounds. So this is kind of a observation that you want to show that things are converging on an attractor. You should first worry that things are not just diverging. So that they get more and more nonlinearity that just explodes. And so that no that there is no kind of recurrence. And so establishing this involves usually some kind of estimate that you bound the nonlinearity, showing that it's not going to blow up. And one thing that happens on and on is that once you have this, you're going to have some kind of soft tools, like taking limits. Once you know that things not blow up, you can start taking limits. And these kind of soft techniques turn out to be very powerful. But this is usually a hard ingredient that needs to be established first. Okay. Now, this is just an excuse because of I'm talking in principle normalization. For reasons of time, I can only talk about some aspects of normalization. It's impossible to discuss many different aspects. Let me just mention what potential can be, because normalization really is applicable in many different settings. So first, normalization can be interesting. It's not the interest of this talk. Can be interesting to do things in linear settings as well. So you normalize systems, and then you get. Well, I'm going to describe a little bit later. So you're not trying to control the nonlinearity and so on. You start already with a linear situation. Many interesting results have this flavor. For instance, as Etienne mentioned, the concept-disordered conjecture on deviation spectrum for additive-preserving flows is one theorem of normalization of this kind. And you can use, for instance, to bound exponential sums, certain exponential sums, by using also normalization in linear setting, and on and many things. These are just examples of things that happened in a few years ago, but there are really many examples. Another example that I'm going to discuss is for circle maps. It's one of the classical examples, early applications of normalizations, which is Arnold's conjecture in this case, and how it was solved. Another one, I don't explain much because I'm going to do in much more detail. Another one is for interval maps, like those unimodal maps that I'm going to concentrate on, which I'm going to go in very much detail. Renormalization behind universality phenomena, and also, more recently, description of typical parameter values. It's again one of the things that start from the 70s. And so on. Another point that's close to me is interesting applications, just to show something that doesn't look a priori to be related to dynamics, is in spectral theory. There are certain Schrödinger operators which are compatible with different types of phenomena, and where phase transitions happen. And the renormalization gives some information about the critical behavior. And in this case, it's called an issue of the mobility edge of specialists. Gives some kind of very fine information. So far, it's some kind of indirect, but kind of fundamental for kind of a good comprehension of those systems. And I'm really just mentioning a few things that are close to me, and there are many other things. I'm not saying that this is, it's not exhaustive at all, and just leave it like this. So let's start with the circle, and let's start in linear situation, then let's later add nonlinearity. A rigid rotation is a specific map. Let's consider the rotation by alpha, so by angle alpha, and then it looks very simple like this. A few iterates, let's say. Okay. And so the alpha becomes distributed. Alpha is going to be rational all the time. Wow. Most of the time. So let's just discuss quickly how to normalize rigid rotation. Let's look at one. This is a kind of interval between 0 and alpha. And let's spread it here to look at it better. And we're going to look at the first return map to this interval. Turns out to be a discontinuous map. The interval, there will be points that come at different moments of time. One interval A and another interval B. And restricted to each of those intervals, not very difficult to see that you get just a rigid rotation, so kind of a translation, if you look like this. And then the intervals exchange. So this is an example of inter-ray transformation. So this might not look immediately like a map of the same class as the original one, but this is easy to fix by gluing. You have an interval, you can glue the extremes, and you get again a circle. And in doing so, you get a map which if you put the correct Euclidean structure, you have reverse orientation, get the exact number, you get the map at this new circle is a rigid rotation of angle exactly fractionary part of alpha inverse. And this gives us our first renormalization operator, which is this one, the Gauss map. X goes fractionary part of X inverse. Is the renormalization operator for rigid rotation? Is the map associated continuous differential algorithm, of course. And this map, you see quickly that's kind of a derivative bigger than one, essentially, except in one point. It presents the kind of good chaos I talked about. So that's the first example of normalization, good chaos. And so what we know that's behind that the good statistical properties of this map are correlated to kind of statistics of continuous fraction expansions of the disease continuous fraction expansion, continuing like theorems and so on. So that's things that people must probably know about. But let's just stop here and see that our first example, and it's quite in line with the basic schemes that I mentioned. Now, what I want now is to add a bit of nonlinearity to get our first interesting really class for this talk. We consider now the difference of the circle, where you now iterate, I put all at the same time, so you see a bunch of points. And the theory, everything solves this point which says, what's so-called point number theory. It is about founded on the notion of the rotation vector. So now points don't kind of move around the circle always by jumping by the same amount, but still there is an average amount of rotation that they do. There's an average drift that you want to go around the circle, which is called the rotation number, how much it rotates in average. And the theory says that there's a basic alternative first, that either this rotation number is rational, in which case the dynamics is periodic, every orbit is asymptotic of periodic orbit, and let's forget about them from now on, or the rotation number is irrational, of course. And in this case, the combinatorics of orbits is exactly the same as that of the corresponding rigid rotation, with the same rotation number. So you see the way the points of the orbit distributed in the circle, ordered in the circle, is the same for this map and for the rotation. That's the combinatorial theory. This, several decades later, was improved by topological theory by Danjois, who showed that smooth diffeomorphism, there's now a need to start putting smoothness, let's not worry about it. A smooth diffeomorphism with irrational rotation number is in fact topologically linearizable. What it means is that by change of coordinates, you just get exactly a rigid rotation. You just a topological change of coordinates, that is homeomorphism. If you just want to see a functional equation for the linearizability, it means this. That's the one that's written there. So there is this nice, which just means that it's the correct change of coordinate for this. So let us start now that we know that topologically you just have rigid rotations, we can already start to discuss how we're going to normalize. Then it's going to be very easy now that you know how to do for the original. I just take the previous picture and change the labels. I have now the interval, I have the circle now f is acting. I just look at the 0 and alpha, I look at the interval bounded by x and f of x. And I found out that it is, just because it's the same topology, it has exactly the same structure as before. So that's no mystery. And the only thing that happens now, you glue and then get a map of the circle that's going to be, if you do it carefully, there's a slight issue here that I don't want to dwell too much, is that you need to glue it correctly, otherwise you lose the smoothness. It's necessary. There's a natural way to glue x to f of x, just using f. Just use the dynamics and give it right gluing. And let's imagine that in this way, I actually produced a map, a renormalization trace, acting on the space of diffeomorphism circle. It's not far from the truth. So, as we saw, when you did the renormalization to rigid rotation, you obtain again a rigid rotation. So here is depicted this big ellipsis. The big one is this whole space of infinite-dimensional space of circles of diffeomorphism, and then the little circle is just those which are rigid rotations. It's sitting there and is invariant under normalization. Now, the normalization operator has some structure here, because the guys with this. So essentially by definition, the renormalization acts on rotation numbers by the Gauss map. So once you renormalize, you change the rotation number, and the weight transforms precisely by the Gauss map. So this means that the renormalization, so you can imagine, so here I showed guys with the same rotation number, so with some fixed rotation number, and basically, once you renormalize, you go to guys with the same rotation number. So you get some structure of a five-dimensional system over this Gauss map. And now, basically, the key information about renormalization is an estimate of Mann from the 70s now. He showed that successive renormalizations are getting more and more linear, which means here that there is in fact, this invariant circle is in fact the renormalization arc of your system. And now you can interpret those fibers that I saw with the same rotation vector are stable manifolds of guys that go together to the same point. There's a mechanism for this. I just mentioned, I cannot discuss in detail. There is a priori bounds there that if you make correct interpretation. Mann, to say the truth, was not using renormalization language, but it's much more convenient to do that. Basically, he was doing renormalization without perhaps liking it. But basically, so look at this estimate, so there are some stars, there's some kind of a priori bounds that maybe stars that don't work. And then there's some kind of miraculous constellation that gets over what I have about. That shows that higher order derivatives are going to become, to disappear after you start iterating. Okay. So why was Mann doing this? He was not interested in the dynamics of normalization at all, so he had an application in mind. It has to do with the next step of Jean-Joie, to do this move theory. So-called Arnold conjecture. Before Arnold conjecture, we should talk about Arnold theorem, which is that the following. So an analytic diffeomorphism of the circle, don't worry too much about regularity, there must be some regularity, is going to be analytically linearizable. This means that the change of coordinates that you need to make a rigid rotation is in fact an analytic map. If two conditions are satisfied. One is that the rotation number must be very irrational. It cannot be too well approximated by rational numbers. This means some time condition must be imposed. And another is that the nonlinearity is small. Those two conditions are necessary in this theorem. This theorem was obtained by, it's like one of the simplest applications of so-called Kolmogorov-Arnold-Moser method, which is used for the perturbative analysis of the Cauchy-Schwarz equation. So you look at this Cauchy-Schwarz equation just as a functional equation. There are some kind of no, it takes place in some infinite-dimensional space. And you look at near the trivial solutions, which are here, for the actual rigid rotations, and now you perturb it a little bit. And you expect, so there's a solution for the original guy. After you perturb, there might still be a solution if you could apply, if you could control the linear version, the linearization of this equation, and you would have some kind of implicit function theorem to play with. So you have two steps that you must solve appropriately the linearized version. Then there will be the issue of irrationality that would be very, very rational. And then there's some kind of technology to extract this kind of implicit function. It's a very, very powerful tool, but in principle local. By doing this method, you have no hope to try to address something that's very far away. So Arnold knew that the first condition is necessary, not the condition to explain, but really if you don't make some assumption about irrationality, you just have a kind of new number, then this theorem will be violated, the conclusion will be violated. On the other hand, he intuited, and that's kind of a fantastic intuition there, because there was nothing that was indicating in that direction, I'd say, that analyticity has a global nature, which means that this condition of small nonlinearity is not necessary. The map can be very nonlinear as long as the rotation numbers has the good kind. You are going to be analytically linearizable. And that's what Mann proved under a strong definite condition that was later shown by Giokos. Now it's known as Giokos theorem. So, and this gives us a first illustration of using normalization, which is this picture. That's the only picture left for the circle. To make things simple here, we consider the case that I'm looking at a guy who has the golden rotation number. The golden rotation number is invariant by the Gauss map. So this means that this kind of stable manifold, as I said, is just a stable manifold of a fixed point. You have these guys with this rotational number, and this set is invariant, forward invariant, and everything is convergent to this point. Now, and this guy is kind of one of the most irrational possible that you can find. So it satisfies the different condition necessary for the Arnold's theorem. And now just do the following. It's a very simple idea that illustrates this principle of global reduction via renormalization. You start anywhere with lots of nonlinearity, and as the man showed, successive renormalization gets closer and closer to the linear setting. Once you are very close, you can just apply Arnold's theorem and conclude that the deep renormalization is linearizable. And linearization is easily seen to be something that's, in fact, renormalization invariant. Linearization is something that's talking about how orbits look in a very small scale, in microscopic scale, and then simply some properties of renormalization invariant. All right, so that's kind of very important principle, and you see how, of course, how you get such a if you follow exactly how it works, the KM method, it's amazing that by such a simple mechanism, you can just get this global result for something that's so local. Okay. So now we go to our second example. So this all happened in the 7th. There was something else that happened in the 7th that led to the development of renormalization theory in dynamics, which was the analysis of unimodal maps. So unimodal maps, as I said, are maps of this kind of shape. And there are those basic examples that come again all the time, which are united polynomials of this form. X goes to x d plus c. D must be even because we need to have an extremely critical point. And so d equals 2, 4, 6, 8. But I've often been doing with d equals 2 for the big pictures, but the theorems I try to for all d. So most of you must have seen this picture. It's the bifurcation diagram. So what it depicts a kind of related. I took a different mathematization of that maps, mostly because the picture was most easily available there. That this is kind of x goes to r, x1 minus x. And what is this bifurcation diagram? It depicts on the horizon the parameter r. I just look at this kind of interesting range between 2.4 and 4. And in the vertical coordinate, it has the phase space. And then there's kind of interesting picture that's remarkably complex. What's depicting, I don't know exactly how they did the picture, but what's supposed to depict is that you start with a point in your phase space and look where it's going, so the limit set. And then you plot it in the vertical coordinate. And do this for each r, and then you get this picture. Of course, different points might be doing different things. Let's look at a generic point in this case and see what's happening. And then basically generic points are going to do all the same thing, and then you get a nice picture like this. So, let's just observe that the pictures get very complicated on the right side for talking about point, but on the left side it looks perhaps comprehensible. So we're going to start on the same side, the left side of parameter space. Let's not try to do something too much immediately. So there, indeed, things are very simple. You start with an attracting fixed point, which is easily illustrated. This is kind of actual dynamics. You have this kind of green fixed point that attracts an orbit that's arriving there. This situation is stable. I changed a little bit the parameter increasing, and the attracting fixed point is still there, still green. Sorry. There's some convergence there. But after a little bit more, something new happens, and there's the first bifurcation. The fixed point has become repelling now, but appeared at the same time a sign for period 2 that turns out to be attracting. So you just see how it goes. It goes near the red point, but then it's expelled to the green point. And they start oscillating between those 2 points. It's still quite simple. Ruled by periodic behavior. This continues for some time. This periodic cycle persists. And later, a new bifurcation happens that's quite similar to the previous one. The green cycle became red again. But now a new green cycle appeared now with period 4. And things converge to this side. And so on. So that explains what's going on the left side. Originally, you have just one point that you're aiming at, and then you bifurcate, and now there are these 2 points after the parameter 3 dot whatever, and then near 3 dot 4 something, there's a new bifurcation with 4 points, and then later 8 points, and 16, and then you cannot see anywhere because things are converging very fast to some kind of limiting behavior. Believe that this happens many times, and converge to something. The limiting behavior is the first time that you get non-periodic phenomena. Up to there, you have increases in the periods, increases in large periods, but always 8, 16, and so on, but the dynamics is periodic. At this point, the period becomes 2 to the infinity. And it's the first time that's actually not periodic, some kind of limited periodic dynamics. And afterwards, immediately we start saying lots of black. And that's when things start to become wild. So let's just draw quickly how this limiting behavior. I took the second iterate here. And it doesn't quite have an attracting point, but it has at least an interval that comes back to itself. It's actually a renormalizable map. And of course, renormalization must appear here. And then again, if you look at the fourth iterating, you are going to not have an attracting periodic cycle period 4 because you pass it by bifurcation, but you have an interval that's still invariant, and so on. You get an interval period 8, and you get this structure. And now, if you look at what's happening to those kind of, what you're actually constructing, if you let the actual dynamics of act, that the initial have an interval that's taken to his companion and comes back. And then inside it, the second iterate will have its own structure that mimics the original one. And this will continue forever. And what you're going to get actually is this kind of 2 to the infinity periodic form. It's actually translation by 1 in the ring of quad integers. That's the natural limit of the sequence of period doubling combinatorics. You just think about combinatorics, and it actually happens at some kind of topological level. So this is actually a theorem that it's beautiful. All right, so that's just and clearly this kind of maps that appear in this transition are infinitely normalizable. You repeat and then you see this kind of normalized period 2 infinitely many times. So, but what kind of phenomenon is called the Spiegel-Multiplicity phenomenon that many people heard about? It's the fact that we have all those bifurcations of period 2 to the n, 2 to the n plus 1 and so on, so let's call them Rn, they're converging to some kind of limit from R infinity. And this happens at a geometric rate, which is one. Fair enough, but what's really surprising is the fact that this kind of constant turns out to be universal. If you take a different family, still with quadratic critical point, and which satisfies some isosceles condition, let's say, just to avoid problems, let's just take the quadratic map x square, add some kind of sign, epsilon sign x, to get a new map, which will still be a uniform map. And what you're going to have is that you are going to have a new sequence of bifurcations, R to the n or something. And they'll be completely different from the original ones. They'll be made by different kinds of equations and so on. The original ones are algebraic, maybe now we're going to get some kind of transcendental numbers. And it's not important at all. What's important is that the rate is going to be not narrowly similar if we make some epsilon change. It's exactly the same. And you can make even a large change and look at a map of critical point that's quite far. And so if you now consider something with a critical point of order 4, if you look at x4 plus c, you no longer get this constant, but you still have universality that you get a different constant. There's still a geometric rate. And this constant will be the same for all maps which have this kind of same criticality. So you have this kind of universality, each criticality, and this is what was discovered numerical by those people. Now, their name are associated with this phenomenon not only because they discovered it, but they actually advanced the mechanism that would explain it, which is the renormalization mechanism. It was they were kind of coming from physics, so it was really inspiring. I'm not going to talk about that, but this is one place, original place where they had this inspiration. And there are several issues to be taken into consideration. I don't want to try to explain the story. This happened before I started working on this, and we are unable to do it correctly. Let's just mention that the first aspects started being addressed by Mumford by rigorous computer-assisted methods. Let's just see how is the universality mechanism. You have a family, and you want to understand what's happening at this moment of application, the onset of HYDEREBAD. So you have this family. So let's imagine that what you're really interested in, there is this region. So let's think in infinite dimensions. So there is some kind of membrane that separates periodic behavior from this kind of complications that appear after. And there is this membrane, and you think as kind of bifurcation. The moment that your family that was is crossing this membrane. Now, this membrane will consist precisely of those kind of infinitely normalizable maps, as we saw how the dynamics at that moment. Now, this membrane is accumulated by membranes that have this kind of period to the n, period to the n plus 1, and then we have sequence of accumulations. And you are looking at this kind of intersection trying to see how they are organized. And what does this normalization do for you? Again, the idea of rescaling of time, that the time for the renormalized guy is twice as fast, or in the appropriate sense, faster or slower, as the original map. It means that if you have a periodic orbit of period 2 to the n plus 1 for your original map, it becomes a periodic of period 2 to the n for the renormalizable map. So renormalization schematically takes this kind of membrane and puts it to the next one. So that's this kind of exploited feature. And the basic renormalization conjectures are that in fact this inside this membrane there exists a unique fixed point for renormalization. And this is kind of fixed point will attract along some directions. In fact, along all directions but one. And you will attract precisely this membrane, which is going to be the stable manifold of the map. And you have an expanding direction the other way. Topologically, it's quite clear that there should be some expansion, some things being pushed out. And this should be really given by some rate that's bigger than 1. So it should be the pictures of hyperbolic fixed point with index 1 or something. So that's the conjectures that must prove somehow. But once you have these conjectures, what we are going to see why there is universality, you have this basic picture. I draw the stable manifold, I draw the unstable manifold. The unstable manifold for the guys that was renormalized in the past, you are going to get close to your fixed point. Now you take this family F lambda that's going there. And then interesting what's happening here, this kind of intersection with the membrane. And what I do, I normalize, and then again, and then again. And as it turns out, this kind of little window will go to something that's very must becoming close to this exactly unstable manifold. This is basic hyperbolic theory. It's kind of you could do infinite dimensions, basically the same thing in infinite dimensions. And what happens by hyperbolic theory is that this transition from this kind of micro window to this microscopic scale has, well, it should be some iterator, not just R. This transition has kind of doesn't distort things. Because of exponential behaviors that are adding some exponentially decreasing things, in the end you get something that doesn't distort things. And so you see that what you see in the microscale is exactly the same as you see in this kind of unstable manifold. And this unstable manifold doesn't depend on which family I started with. This explains universality. And what's going on in the unstable manifold is of course given by the constants that you must find are precisely given by this unstable eigenvalue. So that's kind of explanation of what is thinking about constants, the unstable eigenvalue of this fixed point normalization. Of course, there are many aspects of the renormalization conjecture. First, you have to work on some suitable functional space. Otherwise, your operator will not even be differentiable, and not much things will make sense. But everything is implicit that you should find the appropriate set and work with this picture. All right. So, but period W is just the start. It was just discussing the tail end. And you have all this bifurcation diagrams to understand still. And beyond period doubling, you have other kinds of normalization. This map here, it's not going to be the normalized of period 2. Don't find this kind of little window when you do the second iterate. But it's going to have a little window for period 3. I drew the third iterate here. This little corresponding interval, it will go once to the right, and then once to the left, and then comes back. So it will come back in time 3. And you have this basic structure. Now, if you start to do things, now once you get this, you get again you know the map. You get you know the map. This can be anything. So it will be renormalized of period 2 now. And then you could have an infinitely normalized map that has some very different kinds of periods. The resulting dynamics would be a more general translation on compact group, on a counter group. But again, it is some kind of zero entropy dynamics as you would expect for infinitely normalized maps. So you see that there is this other kind of normalization. And now we have just at this moment understood some kind of piece the renormalization peak. Let's now try to incorporate everything. So all those different kinds of renormalization that there are, clearly the domains stay connected, there's period 2, there's period 3. And I want to show you, before getting exactly what's here, one must understand one model of good chaos, which is Mays model. So first you have this kind of hyperbolicity that you take this square, and then you kind of shrink in the horizontal, and then make it big in the vertical. If I just put this kind of rectangle over the square, I'm going to have just a simple fixed point. That's the picture that I just saw, a hyperbolic fixed point. But now I do something else. I introduce a fold. And now I put it on top of this square. And this is a space horseshoe, which when you iterate, it starts displaying some kind of high complexity. And turns out that this is maybe because it is chaotic, but it's robust in several respects. It's a model of good chaos. And here you're going to see that basically, by looking at how points go from the left to the right side of this horseshoe, you can find some appropriate holding by being infinite binary sequences. So that's the appropriate holding that you get here. And then there's much more to say about the horseshoe. I just want to say that to say that this is a model of good chaos, because now I have the complete renormalization dynamics that be slightly more complicated. So how is it? So we start with period 2. The pictures that there was some space of guys that normalize period 2, and there's some basically hyperbolic pictures. There's a hyperbolic fixed point, and it goes like this. And then if you're interested in the window that intersects with some specific family, it's possible. Let's just worry about the infinite dimensional picture. And then you notice that there is also the renormalization of period 3, gives us a new domain of renormalized guys of period 3. And renormalization will act kind of qualitatively in the same way. Let's just imagine that it's doing like this. And at this stage already, you already have the potential complexity of the horseshoe. It's missing the turn, that's completely irrelevant. This is already, since you can go from the left to the right, from the period 2 to period 3 and so on, you get all the kind of this kind of binary expansions that are possible. But of course, there is also some other window that you have period 5, which would behave in the same way, qualitatively, and so on. So in the end, the appropriate model for this looks to be some kind of full horseshoe, would be meaning that the dynamics of the conceivable attractor should be coded by being infinite sequence of natural numbers. It's not the extension idea. Now, to have the structure of the horseshoe and all those rows and so on is not only this kind of topological thing, it involves some kind of considerable amount of geometry, of how all these contractions and expansion match together. So, the basic theorem of the renormalization dynamics is that there is a renormalization attractor that's a global attractor. Any infinite normalized map will go to the renormalization attractor. It's going to be precisely given by this coded by this infinite sequence of natural numbers. And it should be have basic properties of Mays horseshoe that's uniform hyperbolicity that makes it stable, allows you to study the dynamics. So this theorem was, there's a long story. There was much work by Sullivan, McMullen, and then Lewis to work on the case of bounded periods. So just incorporate finitely many pieces of the picture. Then I certainly cannot explain why quadratic is different from hybrid. You know that sometimes numbers matter, and here d equals 2 is special. So for some geometric reasons, it was possible to treat the case of quadratic critical point, and then more than 10 years later, we did defend this the general case. It's kind of the last part of the paper is not out, but it will be eventually. So what is it useful for? So now I'm always saying some renormalization dynamics, and then I say why it's used. Well, it's used in the sense of typical unimodal dynamics. So let's see still one more kind of unimodal dynamics. We already saw periodic, and for the moment we saw that there was kind of limit periodic dynamics that appears sometimes associated with infinitely normalized maps that are kind of local, that there's a zero entropy attractor, but it's not periodic. So this guy is now in the other extreme, on the wild side. Look at the top map with parameter 4, and the data goes all the way to the top. And this map turns out, if you do just 4x1 minus x, is conjugated by a kind of very nice change of coordinates, is an analytic point, exactly to the stamp map. This stamp map here, full stamp map, is obviously has positive Lyapunov exponent. The derivative has absolute value 2 everywhere. It's basically the binary expression map, except for some kind of change in mathematics. So this map here is going to be one of those kind of good maps that you're going to try to analyze probabilistically. Let's call this map kind of map stochastic. It should have positive Lyapunov exponent, or should be distributed with respect to some kind of nice measure of spontaneous and so on. Those maps are not a problem. They are nice. So then Jacobson's theorem is the first explanation of blackness in the picture. It says that this kind of stochastic behavior contaminates a little bit nearby and creates near this parameter 4, there's a positive measure set parameter where you have other stochastic behavior, which means that the points are going to be kind of quite fuzzy and going to be filling intervals. The limit set to be filling intervals and give rise to all this blackness. And still, you get kind of things that not as easy as periodic, but quite good to work with because of precisely those techniques. So the use of renormalization, so now one thing that renormalization uses is, okay, let me just mention that. So for the moment we saw three behaviors, I think. There was periodic, this is kind of infinitely normalizable, and now stochastic. And I must say that there are other behaviors I cannot explain that are kind of very pathological. The dynamics of modal maps kind of is compatible with some things that are very weird. And a general principle in dynamical systems that, well, we should perhaps try to understand everything, but very that's also good to try to understand what happens for typical parameters, what happens for most systems. And this kind of very mainstream part of dynamic ideology of dynamical systems, you should ask what's the behavior of a typical unimodal map. And this is answered by this theorem for, I'm going to try to in a moment, that for almost every parameter, you either face periodic behavior, I'm calling regular periodic behavior, or everything goes some kind of periodic, almost everything. Or you find kind of nice stochastic behavior. So this theorem was proved, this theorem used the theorem about the full renormalization portion, so it was proved for d equals 2 by Liouville more than 10 years ago, and here's the general case. No, it's more recent. So what does this have to do with renormalization? It's the part that says that this theorem is essentially saying that infinitely normalizable maps, which are neither regular nor stochastic, must have correspond to zero measure set of parameters. And so how to make, let me show just quickly the mechanism for this zero measure set. This is gap spreading. You are trying to understand one specific renormalization parameter, let's say, so your parameter that is infinitely normalizable, it is in a little window of your family. And after renormalization it gets big because of this expansion in that direction. And then it's renormalizable again, it gets to a different window. And then again and again. And then you have basically this picture. And the transition map, because of probabilistic, just like in the situation just a fixed point, the transition map from this kind of tiny windows to the microscopic scale does not distort much things. So downstairs, you have this gray area that says that in the same end, you have attracting points. So by pulling back those kind of regions, you're going to get some gray areas in the renormalization windows, corresponding now to periodic points, the corresponding period involving the renormalization. So this is kind of inside the little window will appear finally an attracting fixed point, which makes things regular. Now, the fact that you don't have distortion means basically that near each infinitely normalizable map, you're going to find gray regions in naturally small scales, which basically means that there cannot be any density points. And hence, since there are no density points, the set must have zero by measure. So just quickly showing how you can use dynamics here, basically this bounded distortion property. And then we can go to, once you have this renormalization factor, we can look at more other aspects of the dynamics. I shows one particular theorem that you can look, for instance, at fractal geometry, and by analyzing it, some kind of information that gets to this theorem that says that the half dimension of exceptional parameters is in fact strictly between 0 and 1. The hard part showing that's less than 1. So that's an example of application. let me mention quickly what's the mechanism of convergence, just to give you an idea. Here, the situation is completely different from the circle case. In the circle case, you have the attractor a priori, given by a formula. Those are maps that are linear. For the in the situation of unimodal maps, the maps that you're going to obtain, they're going to be highly transcendental. They're going to be located. They're not going to be given by some simple formulas. So you have the problem of construction of the renormalization attractor. So the construction of this attractor, in fact, can be done at the same time as we establish convergence in the following way. It turns out that just as for circles, there are some candidate stable manifolds that are defined here. There is by the rotational number. Here by some kind of quasi-formal deformations of the dynamics. You have complexified the dynamics and produce quasi-formal deformations. But there is a way to introduce candidate stable manifolds where you should get a contraction. And what we will do then is to use so-called a priori bound to allow you to take limits. So, but in this new approach that turns out to be more general than the previous ones, you don't no more just apply renormalization orbits, but look at iterates of renormalization as kind of function. And you take functional limits of renormalization iterates. So you're going to try to use some kind of Scalia-Hazela theorem and so on to get some kind of functional limit of renormalization. And now you get a bunch of properties of those functional limits. And so it's a map of a certain kind, of a certain space to itself. And you can check that for based on topological reasons, so something that is of a global reason here for the dynamics of normalization, not just looking at two orbits, but looking at all orbits are necessary. That the topology of the candidate stable manifolds, the deformation space is going to be intractable, will force collapsing. So this limiting map must be a constant map in the two orbits. So this is the new approach that, because usually people look at 2 points. That's kind of thing that was done to a large extent, is to try to find good reasons for those maps, geometric reasons for those maps to get closer and closer together. Here, you don't look at those 2 points, you look at all points at the same time. And do this. Okay, so we're going to just mention quickly that beyond this talk, the renormalization in a linear setting, as I said, will lead to interesting finite-dimensional dynamics. So the kind of things I mentioned, that I said that I wouldn't be able to describe in detail, I can at least list what is it about. It's things like the geodesic flow on the modular surface that's related to the continuous fraction algorithm. And the higher dimensional analog, the tight million flow normalized space of billion differential, that's what the concept conjecture is talking about. Another example of this kind of exponential sums is the use of normalization in the study of Heisenberg new flows. And now, to conclude just about the last part, it should be quite quick. I didn't know that I would be able to get there. So if there is application of one-frequency Schrödinger operators, I won't be able to talk at all about the dynamics, but just to give an idea of how it can be dynamics renormalization can be applied quite far from what we started with. So I have kind of operator of this type. That's not a word too much, but it's a Schrödinger operator, so you're interested in the quantum dynamics. You do this thing, take exponential IT8, and then make T grow. So this is some kind of quantum of dynamics in this state space kind of lattice, one-dimensional lattice. And you have some kind of wave that you are kind of letting evolve under the same group. And there are kind of two kind of nice situations. One is localization, when the wave stays more or less in some region of space and doesn't kind of spread to infinity. And there's also split of transport. And especially the fastest kind of transport, the wave just starts moving around to infinity, the mass kind of is going away. So that's the split of transport. And the data is of particular kind. So you see that there is some kind of quasi-periodic dependence there. The V of n alpha is a rational number. And V is a periodic function. For this kind of system, it allows both localization and ballistic motion. For large V, you have localization. For small V, you have this kind of fast transport. And this is quite remarkable. There are other systems. One of the most famous systems where we expect this is so-called undermodel in 3 dimensions, where it's a kind of lattice, kind of very natural system. Unfortunately, there is no mathematical theory that can address transport here. But here you have something that there is a mathematical theory, and you know that those two behaviors are there. And now let's study how you can transition from one to the other and get into issues of phase transition and so on. I should not, so this is just kind of last two slides. I want to discuss this. There is an associated dynamic system somehow, which is renormalizable. And there is a renormalization dynamics, which is kind of different from that of in the Riemann situation. There's no more a global attractor, but a local attractor that you capture the behavior for small v. But for large v, it will not be captured because of some reason such that the tip of the Lyapunov exponent. Now, renormalization is not a kind of, so now we no longer are looking for proving some kind of global versus renormalization. Renormalization has its limits. And then your preoccupation now is to try to understand what's precisely the subtraction from convergence and renormalization. And here, what turns out that gives indirect information about Fetro interface that should separate these two kinds of ballistic motion from localization. And then you can know what it means. So there is phase transition, what role it has for operating. So you understand small kinds of V, large V, what happens for a typical V that might be in intermediate range. And so renormalization is one part. There's kind of many different parts on this puzzle. But one part is the use of renormalization to get eventually, which is to get this kind of spectral dichotomy. That's a basic structure theorem of data that has been obtained quite recently in my work. Maybe I still write the details. That says that there's a general simple structure for the operator, that you don't need to worry about phase transition. A typical one-phase operator is a direct sum of a large part and a small part. So that's kind of a basic your Hilbert space decomposed into two parts. So basically, the wave that you're trying to analyze, there will be one component that's going to move ballistically and the other component that moves localized, and there's no component that kind of oscillates or something strange. Okay, let me just show a picture that illustrates this. This is a particular slice of the critical region. This is not entirely consist of critical things. Actually, everything that's colored is kind of not critical. And what is kind of not colored, that you cannot see where the colors change, which is very thin, and that's why you don't see it, you just see that the colors are changing, is actually the region of phase transition. What renormalization says in this infinite-dimensional constant, here kind of has been analyzed, is a statistic model that is corresponds to some theorem of last, what I'm going to say. But the corresponding thing in infinite dimensions that is possible to say is that inside this kind of membrane where you are supposed to find critical phenomenon, the actual critical points have zero measure, essentially. And due to this kind of smallness of this critical region that you can control using renormalization by indirect approach, you get this typical Schrödinger operator. Now, I should mention at least one open problem. And here is so this picture is very beautiful. It clearly has some self-similarity features. The usual renormalization operator about what I was talking about, that has some local attractor that's very same than the other things that diverge, doesn't tell you anything about what's happening at the critical point. The information is indirect. It says what cannot happen. Cannot happen that this has too much, corresponds to too many parameters. But it would be great to try to really give some kind of positive description of this kind of specific dynamical system associated to critical phenomena. But this would involve a construction of a different kind of normalization operator. There have been some attempts on this by Helfer and Jostman, but this is not a dynamic normalization. But it's clear that there is a normalization here, and that's one challenge for the future is understanding of this picture.
Thank you very much, Artur. On behalf of the organizing committee, you have a gift.